Welcome to this small section on how to solve differential equations with methods which give us a higher cutoff or truncation in the Taylor expansion. So one of these family of methods is called the Runge-Kutta methods. So till now, we have essentially used methods like Euler's method, forward Euler. We have modified it with Euler-Kromer, which we have shown is a method which conserves energy. We have also introduced the velocity-Valais method. Now, for many of the kind of differential equations which we encounter in mechanics or in electromagnetism or in other physics applications, there may be a so-called drift term or friction term or air resistance term or whatever we might have as a term which lets the system dissipate energy. So in our case, we have been studying harmonic oscillations where we have a term which is supposed to represent friction, and it's a term which is linear in the velocity, and we see that in the dx dt term. So this is a one-dimensional equation for a spring force. And we have added this term with a parameter b, which obviously depends on quantities like temperature, pressure, and other properties of the system, which then determines how the system behaves under the influence of friction or air resistance or whatever kind of additional force we may add to the system. Now, we can apply an external force as well. So this type of differential equations are differential equations where the system now is dissipating energy. So that means that we could still apply the velocity-Valais method, which has a mathematical truncation error, which goes like the step size, which in our case is the step size in time, which we call delta t. It goes as a step size to the power of 3. Now the question is, do we have methods which give us a higher truncation in terms of the step size? So one set of methods is the family of Runge-Kutta methods. And one of the more popular methods is a method which is called the Runge-Kutta to fourth order. That is a method which has a mathematical truncation error, which goes like delta t to the power of 5. That is the local error, which we make at every time step. Now, the global error is proportional with the number of time steps, which means that the final global error goes like the step size in time to the power of 4. This is still a huge improvement compared to methods like the velocity-Valais. Now, the Runge-Kutta family of methods suffers, however, from one thing, and these are methods which do not conserve energy. So if we are looking after energy conserving methods, the velocity-Valais method, which we have discussed till now, or the simpler Euler-Kromer one, do actually a better job. However, if we are interested in the numerical accuracy within the limited time step, suppose we have a final time which is represented by some few seconds, then the Runge-Kutta method is a method which you may consider using. So what we are going to do here is to give you a brief introduction to these methods and how you can use them in this specific course. So when we have applied an external force, we could apply an external force which goes like a cosine. It doesn't need to look like a cosine force. The things which we have done and which we always end up doing is to manipulate the equations by scaling them. And typically we would scale away time here. So we have a dimensionless time, and we have introduced a dimensionless time, which is now scaled in terms of the natural frequency of the system, which in our case is determined by the square root of the spring constant divided by the mass of the system. So this omega 0 is a system-specific term. When we do that, the equation which we end up studying is an equation which now has this dimensionless time. The equation has dimension position, and we can keep rewriting it by redefining the parameters in front of the velocity, which are now given in terms of this gamma. So we have a pretty simple differential equation here, which we can solve. In this particular case, we can find a analytical solution for as well. As soon as we add nonlinearities to this type of equation, like the mathematical pendulum, what we end up with then is an equation which, in most cases, unless we are looking at small angles in the mathematical pendulum, we may not be able to find analytical solutions, and we have to revert to numerical solutions only. So what we are going to do now is to look at the way we are going to derive this family of Runge-Kutta methods. And the family of Runge-Kutta method, as I said here, they have a global error in terms of the truncation or the time step delta t, which is much better than the standard velocity Valais method. So let's take a closer look at the mathematics behind these methods and how we can implement them. So in the lecture slides for week 10, you will find a set of codes where we have tried to bring together all the different numerical methods which we have been studying till now. But let's take a closer look at the family of Runge-Kutta methods. We're now going to meet the family of Runge-Kutta methods. So to get started, let's now look at what we would call a first order differential equation. So we have a quantity y, whose first derivative we are interested in applying to the right-hand side, where we have a function, which is a function of t, time, and y. We do not need to look at time as a specific variable. So t could represent another type of quantity, y could represent another quantity than position, and so on. So when we use one of the fundamental theorems of calculus, we know that when we integrate this up, this is given by y of t, and this is given by an integral over ft of y of dt. So we're putting primes here. Now, when we integrate this from a time ti to a time ti plus 1, this is now going to be given when we now discretize these equations. So we're going to discretize this to a y of t of I, and we use the shorthand y of I. So when we integrate this equation here, what we're going to have is a y of I plus 1 is equal to y of I plus an integral which goes from t of I to a t of I plus 1 multiplied with the function we want to integrate, which is the right-hand side of the differential equation. So this is a pretty basic transformation of the differential equation into an integral equation. Now, the main thing with the Runge-Kutta methods deals with the way we approximate these integrals. So different approximations to the calculation of the integrals leads to different types of Runge-Kutta methods. So one of the more common methods, if we look back at the methods for finding integrals numerically, there's a rule which is called the rectangular rule. And this is going to give us an approximation to the method, which runs like this. So I'm just setting up the mathematical expression first. So we would have a t of I, and this is given by t of I plus 1. And then we have our ft of y of dt. And this is given by a given step size, delta t, multiplied with the function f, which we have. But this function f is now evaluated at a midpoint between t of I and t of I plus 1. So the way we indicate this midpoint is just by writing a half here. But then we need to evaluate the function y of I plus 1/2. And this has a mathematical truncation error, which goes like delta t to the power of 3. When we repeat this n times, if we have n integration points, this is going to give us a global error, which goes like delta t squared. Compared with the velocity Valais or the Euler-Kromer method, this has actually, if we compare it with the velocity Valais, this has one higher power in delta t than the velocity Valais method. So in principle, even if this is a non-energy conserving method, we should, with some few time steps, we should actually be able to get a better precision or better result in terms of the time step delta t. Now you can interpret this method in a very simple way. It's called the rectangular rule. And that's simply because if we look at the integrand and the way we are going to approximate the integral, we are simply going to assume that the area below the curve f of t of y is given by a sum of different rectangular areas. So you can now, if we plot the function ft of y here, so let's just assume this function looks like this. We discretize our domain from a t0 to a final t of n, and we want the area below the curve from t0 to t of n. Now, the way we approximate the area here now is by using the so-called midpoint. So if we now move one step to t1, we move another step to t2, etc., up to a t of n minus 1. Then the area, the way we approximate this area is simply by calculating the area of a rectangular box. And it may not approximate properly the area below the curve, but clearly if we make the delta t smaller and smaller, we are going to get an area which is getting closer and closer to the correct area. Now what you see here now is that if we now evaluate the function at the midpoint, so this will be t0 plus delta t divided by 2. If we evaluate the function at that specific value, this will be the height of the rectangle. And then the width of the rectangle is simply delta t. So this area is given by f of t0 plus delta t divided by 2. And then we are plugging in the value of y, of I plus this delta t divided by 2 here, but we just write it as a half here. And this is multiplied with delta t. Now, the method then, the final area under the curve from t0 to tn would simply be the collections of all these areas of the different rectangles. And they are evaluated at the midpoint between ti and ti plus 1. You get the function value, and then you multiply simply with the step size delta t. So this is a very intuitive method, and it is a method which is similar to another method to approximate an integral, which is called the trapezoidal rule. Now, the interesting thing now is that if we do this, what we have is a method which allows us to approximate the integral in a very efficient way. And it's going to give us now a updated value for y of I at the next time step, which is given by y of I plus this delta t. So this is now the approximation. We are taking away the delta t cubed approximation. So in principle, we should actually have an approximation sign, but we are a little bit sloppy here, so we just leave it out. So we would have a t of I plus 1/2, and then we have the function evaluated at this plus 1/2 value. Now, the problem we should face now is that the y of I plus 1/2, this is unknown. We can obviously calculate t of I at the half time step, but we do not know the value of the function which enters the evaluation of the right-hand side of the differential equation. Now, when we don't know the value of a function, we can actually invoke the simplest possible method which we can think of. And the simplest possible method we can think of is actually Euler's method. So what we are going to do now is to evaluate this unknown function by using the simplest possible method, which is Euler's method, which we have met earlier. And Euler's method simply says that this is going to be y of I plus, but now we have delta t divided by 2, and then we are evaluating the function f of I at t of I and with the value y of I. And these quantities are both known. So this is nothing but Euler's method. So this means that the method we are looking at now is a two-step method. We need first to evaluate the value of y of I at half the time step from the initial point. And then with this value evaluated with Euler's method, we can then go back and calculate the value of the function f. And with that, we are actually correcting the final value of y of I plus 1. So we can look at this in a more geometrical way. So let's make a plot of what we are doing here. So if we are now in a position t of I, and then we want to move to the next position t of I plus 1, what we have then is that we are using Euler's method. So we know the function value here. So we know f of t of I and y of I. So this is something we can compute. We also have y of I, which is known at this specific value. It means that with that, we can calculate the slope here. And this is a slope which is used in Euler's method. So the slope of y is obviously given by the function which we have here. Now, we are using this slope to make a prediction for the midpoint. So we are getting to the midpoint here, which is half the time step. So we use this slope here to make a prediction for this point y of I plus 1/2. Now, what we do next, if we now look at the equations, we are now going to make a correction to this slope at the midpoint. So we get an estimate for the midpoint value of y. This estimate is now plugged into the equation here. And then we get a new slope for the function y of I plus 1/2. So we get a new slope here. And then we use that slope to make a prediction for the final point y of I plus 1. So this is a two-step stage if we are using the rectangular rule to evaluate the integral. First, we make a approximation for y of I plus 1/2 by using Euler's method at the starting point, where we have assumed that we know t of I and we know y of I. This gives us a prediction for the value of y at the midpoint. We then recalculate the slope, and then we use this slope to make an estimate for the final point y of I plus 1. So this is a kind of geometrical interpretation which we can make when we are implementing this method. Now, from a calculational point of view then, what we end up with is to have to calculate some specific quantities. And you will often see in codes for the Runge-Kutta method that people introduce a quantity which we would call K1, which is now delta t times f of t of I, and evaluate a t of I and y of I. Then we have a K2 here. So this is our original slope, which we calculate. And with that quantity there, we can now make a new prediction where we now have a quantity which we call delta t with f of t of I plus 1/2, and then evaluate it so that we can find y of I. But now we have y of I plus this K1 divided by 2, because we have half the step size. So we need to take delta t divided by 2. So we evaluate this K1. It gives us the original slope at the starting point. And remember now that the starting points are always well defined because we have to give the initial conditions. And the initial conditions in our case give us either the initial velocity, the initial position, or whatever kind of initial system we are considering here. Now, with that, we are now ready to set up the method. So we would then have a y of I plus 1 equal to y of I plus this quantity K2. And this is a method which is simply called RK2. So this is the Runge-Kutta to second order. Now, the Runge-Kutta to second order is extremely easy to implement, and you will find the implementation in the codes. But there is a method which gives us actually a higher precision, and which is based on another way to approximate the integral. And this method is widely used in numerical implementations. So you will also see that in many cases, people tend to mix Runge-Kutta methods. So you can actually play around with many of these methods in order to refine the step size. So sometimes you may encounter something which is called the Runge-Kutta 4-5, which is a mixture of the Runge-Kutta to fourth order and the Runge-Kutta to fifth order. But let's look at the Runge-Kutta to fourth order. So this is normally called Runge-Kutta 4, or just RK4. Now, in this specific case, the integral which we're looking at is evaluated by another famous formula. And this uses a formula which is called Simpson's rule. And Simpson's rule states that we can approximate an integral from t of I plus 1, and we have the integrand here, t of f of t of y of dt. And this is approximated now with an integral which goes like h divided by 6. No, not h, sorry for that. There's a delta t here. That's nice, our step size, delta t. And it contains the function value at the initial point, t of I, y of I, plus 4 times f, evaluated at the midpoint, t of I plus 1/2, t of y of I, evaluated at the midpoint, y of I plus 1/2, plus the function evaluated at the endpoint. And you see clearly now that we don't have the function at the endpoint, and we don't have the function at the midpoint. So the Runge-Kutta to fourth order is a method now which reorders a little bit this integral and uses first Euler's method to make an estimate for the value at the midpoint. And then it recalculates the slope at the midpoint and uses that slope to make a prediction at y of I plus 1. So there are going to be some more intermediate steps. This method here has a mathematical truncation error, which goes like delta t to the power of 5. So it means that compared with the velocity relay method, we have 2 orders of magnitude higher in delta t. So think of you running the velocity relay method, which has a truncation error, which goes like delta t cubed. If your step size is delta t is equal to 10 to the minus 2, 0.01, then your truncation error with the velocity relay method would be 10 to the minus 6 times some constant. If you're using the Runge-Kutta to fourth order method, your truncation error would go like the time step to the power of 5, which gives you 10 to the minus 10, multiplied with some constant. So in principle, we go then from 10 to the minus 6 to 10 to the minus 10. So this is one of the advantages of these methods. So the Runge-Kutta method is also a method where you don't need that many more function evaluations. So let me show you how people actually have developed this method. And these kind of manipulations, which you're going to see now, are pretty common within the manipulation of differential equations. So what we are going to do now is to rewrite that term to the right here in terms of 2 terms at the midpoint. And this is, by doing that, we are going to then have 2 evaluations at the midpoint, which allows us to correct the slope of the midpoint. So the recipe itself is going to be given by y of I plus 1. So this is given by y of I, and then we have the integral here, which goes like delta t divided by 6. And it has f at t of I, y of I, plus, but then we evaluate the slope at the midpoint twice. So we're going to t of I plus 1/2. This is going to be given by y of I plus 1/2. And then we simply have a new term evaluated at the midpoint of t of I plus 1/2 of y of I plus 1/2. And then we have the final point, which is given by f at t of I plus 1 of y of I plus 1. And the mathematical truncation error is something which I'm skipping now. So in principle, I should have put an approximation sign instead of an equality sign here. But I'm dropping the delta t to the power of 5 term. Now, again, the problem which we have is that we need to define the first approximation at the midpoint in terms of Euler's method. So what we are going to do now first is to repeat the same step we did with Runge-Kutta to second order. So that means that we are going to approximate y of I plus 1/2. So let me just write this better. So we would have a y of I plus 1/2 is now going to be approximated by y of I plus delta t divided by 2 and multiplied with the slope at the initial point. So this is something which we defined previously in terms of this function k1. So we had this function k1, which we now defined as a delta t times f of t of I of y of I. Now, what we're going to do now is that we are going to re-evaluate the slope at the midpoint. So it means that we're going to get a k2 here, which is the same as we did with the Runge-Kutta to second order. So this k2 term is going to be given by a delta t of f, and then I have my t of I plus 1/2. And then what I have now is y of I plus this k1, but divided by 2, because I have delta t divided by 2. Now, what I do next then, so this is my first step, and these manipulations are going to enter this term here. But then, since I'm evaluating the slope at k2 again, at the midpoint, I'm going to reuse that one to re-evaluate the midpoint. So this is a two-step stage. So it goes beyond the standard Runge-Kutta to second order, because when we did the Runge-Kutta to second order, we extrapolated from the midpoint to the final point. Now we are going to adjust the midpoint twice. So that means that we are going to compute a new slope, which is now going to be given by this function k3, which is given by my delta t times f. I'm still at the midpoint, plus 1/2. But now I'm going to calculate y of I plus this term k2 divided by 2. So I'm improving my guess for the midpoint. And then finally, I'm going to use these values to extrapolate to the final point. So I'm going to define a new function, which is going to be given by my delta t times f. And then I have my t of I plus 1. And then I have y of I plus this function k3, which is now an improved derivative at the midpoint. And I use that improved derivative to make an estimate of the final value, which is y of I plus 1. So if we look at this from a graphical point of view, let's go back again to what we had in the RK2 method. So we have a t of I. We go to the midpoint, t of I plus 1/2. And then we end up with a final point, t of I plus 1. Now, what we do now is that at this point here, we evaluate this quantity k1, and we evaluate y1, or rather not y1, but y of I. So we have a k of I, and then we have a y of I. So we know the value y of I, we can evaluate k of I, and that gives us slope here. Now, the first thing we do now is to make a prediction for y of I plus 1/2 And we predict also this quantity, or we calculate this quantity, which we call for K2. So this gives us a new slope. And then we use this slope again to correct the value for y of I. So this could give us a new value for y of I plus a half. And we then calculate the new slope, k of 3, which is used to predict the final value at y of I plus 1. And then we use this value y of I plus 1 to calculate the slope at y of I plus 1. So what we are going to do then is, in a way, to take a kind of average of 4 different slopes. So we have one slope here, which is our first guess. We improve the slope here. And then finally, we calculate the slope here. And the final result is now the combined average of all these slopes, so that we end up with an equation for y of I plus 1, which is going to be equal to y of I plus this delta t. Actually, we have included delta t in the functions k now, so we have to be careful. So this should actually be just 1 divided by 6. And what we have then is the first slope, k1. We have 2 times k2, the first estimate of the slope at the midpoint. And then we correct it with a 2k3. And then we have finally a k4. And what you see here is the recipe for Runge-Kutta to 4-folder. And this concludes the derivation of the methods. So just to summarize, these methods are based on different algorithms for evaluating an integral between t of I to t of I plus 1. Based on these algorithms, you can get methods with different truncation errors. So the RK4 method is a method which strikes a compromise between the truncation error, which in our case goes like delta t, a local truncation error to the power of 5, which is 2 orders of magnitude better than the velocity-Valère method. And the only thing we need now are 4 function evaluations. So there's always a compromise between the number of CPU cycles you are willing to invest and the truncation error which the different methods offer. So in the slides for week 11, there is an example of how we can actually collect the different methods in terms of various functions. So what you would find then is first Euler's method. The difference now is that we have defined a function where the force is given. So in this specific case, we are transferring an array with the velocities, the positions, time, the number of integration points, and a link to a function which evaluates the specific force. Here we have defined the spring force in 1 dimension. You can obviously modify these methods to include 2-dimensional or 3-dimensional systems. You can add other types of forces. And then that means that you would simply just use that specific force, which is the one of interest. So these methods are pretty generic now. The only thing they need is a call to a function where you have specified the force. And that takes in as input a pretty general situation, which contains the velocity at a given time step, the position, and obviously time. And this is simply Euler's method. You can then add the forward Euler chroma, where we now have an update of the position in terms of the new value of the velocity. This is an energy conserving method. We have already discussed the velocity-Valère method, which is encoded here. So all these methods here, they take the same type of input. They have velocity, position, time, number of integration points, and the link to the function which defines the force. And with the force, we can then calculate the acceleration. And with the acceleration, we are then set to update the velocities and positions. Now, the next equation which you see here is or the next code here encodes the Runge-Kutta, the second order Runge-Kutta. And you can see now that it sets up a K1 term, which we discussed in the slides, for the X, for the position and for the velocity. And it updates velocities and positions at the midpoint. And then it calculates this K2. And then we have the final value, which is simply this K2 in the X direction and K2 in the velocity direction. since we have a second order differential equation, which we now have rewritten in terms of two first order coupled differential equations. And then finally, what you will find here is the Runge-Kutta fourth order. And then we simply need to make some further evaluations. So we need this function K1, which calculates the slope at the beginning, K2, which is the first attempt at the slope at the midpoint, K3, which is an improved slope, and K4, which is our guess for the slope at the final point, and then the final result, which now is an average of all the different slopes which we have calculated. And this code here is something which you should feel free to use as much as you want. So when you are solving differential equations now, you have a set of methods which you will also encounter when you use packages like ODEint in Python. These packages, they contain many of these differential equation solvers and many more, obviously. But these are some of the most used methods in solving differential equations. So if you have a type of equations like this harmonic oscillation type of equation with a dissipative term and applied force, what many practitioners tend to use is a method like the Runge-Kutta fourth order, or a mix of the Runge-Kutta fourth order and fifth order. And these methods strike a good balance between numerical accuracy and the number of CPU cycles you're willing to invest. So feel free to use these methods in all exercises and midterms which are to come in Physics 321, and best wishes to you all.